Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay. The 1909 Nobel Prize in Physics recognized Russell Allen Hulse and Joseph Hooton Jr.'s discovery of a new type of pulsar situated within a binary star system, designated Pulsar B1913+16. This groundbreaking contribution to astrophysics furnished the first observational confirmation of gravitational waves, as postulated by Albert Einstein's general theory of relativity. The ensuing essay undertakes a meticulous examination of Hulse and Taylor's seminal publication, a new binary pulsar, published in 1975 in the Astrophysical Journal Letters. This analysis proceeds section by section, dissecting the core claims, assessing the evidentiary basis and evaluating the wider implications of this landmark discovery. Section 1, Introduction and Observational Context. Hulse and Taylor initiated their paper by underscoring the novelty of their discovery, a pulsar residing within a binary system. Existing pulsars were, at the time, typically understood as isolated, rapidly rotating neutron stars. Locating a pulsar in a gravitationally interacting binary system presented a unique opportunity to probe strong field gravity and refine our comprehension of these celestial objects. The authors highlighted the Arecibo Observatory as the instrument crucial to their finding. The telescope's immense collecting area permitted the detection and precise timing of the pulsar's radio emissions, a feat that would have proven exceedingly difficult with smaller instruments, though initial claims centered on the identification of periodic variations in the pulsar's pulse arrival times, suggesting orbital motion. These variations presented a clear departure from the previously observed behavior of solitary pulsars. Section 2, Discovery and Initial Parameter Determination. The subsequent section of the paper details the process of identifying the pulsar's binary nature and establishing initial orbital parameters. Hulse and Taylor meticulously describe the data acquired at the Arecibo Observatory, focusing on the systematic changes detected in the pulsar's period. The Doppler effect, a fundamental principle in physics, served as the key to interpreting these variations. As the pulsar orbited its companion, its motion toward and away from Earth caused apparent shifts in the observed pulse frequency. The magnitude of these shifts enabled the team to calculate the orbital velocity of the pulsar, while the periodicity of the shifts directly related to the orbital period. The authors determined the orbital period to be approximately 7.75 hours, a relatively short period suggesting a close proximity between the two celestial bodies. Further analysis permitted preliminary estimates for the orbital eccentricity, quantified as 0.6 to 1. Signifying a markedly elliptical orbit. This high eccentricity assumed significance later when the predictions of general relativity were considered. The mass function, a crucial parameter derived from the radial velocity curve, provided insight into the masses of the two stars, albeit with a dependence upon the orbital inclination, an angle difficult to ascertain directly. Their claim of high orbital eccentricity was meticulously supported by the precise pulse arrival times. Section 3, Timing Observations and Data Analysis. This segment chronicles the meticulous process of timing pulse arrivals, a vital undertaking for extracting precise information about the system. Hulse and Taylor elaborate on the instrumentation and techniques employed to measure the pulse arrival times with remarkable accuracy. They discussed the importance of accounting for various effects, including the Earth's motion around the Sun and the effects of interstellar dispersion, which delays radio signals as they traverse the interstellar medium. The authors emphasized the creation of a timing model, a mathematical representation of the pulsar's behavior that incorporated its spin period, its position in the sky, and the parameters of its binary orbit. By comparing the observed pulse arrival times with those predicted by the timing model, they could refine the parameters and identify deviations from the expected behavior. Sophisticated algorithms facilitated the fitting of the model to the extensive observational data. The team asserted that the consistency between the observations and the timing model validated the proposed binary nature and established a solid foundation for further investigation. The accuracy with which they measured pulse arrival times, down to fractions of a millisecond, represented a significant advancement in observational astronomy. Section 4, Relativistic Effects and Orbital Decay. This section presents the most groundbreaking claim, the observation of a decrease in the orbital period of the binary pulsar, interpreted as evidence for the emission of gravitational waves. Hulse and Taylor detailed how their long-term timing observations revealed a systematic shortening of the orbital period. The observed rate of decrease, quantified as approximately 7 to 5 microseconds per year, could not be explained by classical physics. The only viable explanation, they argued, was the emission of gravitational waves, as predicted by general relativity. According to Einstein's theory, Accelerating masses should generate ripples in spacetime, carrying energy away from the system. In the case of a binary star system, the emission of gravitational waves would cause the stars to spiral inward, resulting in a decrease in the orbital period. The authors demonstrated that the observed rate of orbital decay closely matched the predictions of general relativity, providing strong support for the theory. This constituted the first empirical evidence for the existence of gravitational waves and a rigorous test of general relativity in the strong field regime. The agreement between the predicted and observed orbital decay rates was profoundly impactful. Section 5. System parameters and nature of the companions. This section delves into the estimation of the masses of the pulsar and its companion star. Hulse and Taylor recognized that the mass function alone did not provide sufficient information to determine the individual masses. However, based on the observed relativistic effects, specifically the advance of periastron, the point of closest approach in the orbit, they were able to place tighter constraints on the masses. The advance of periastron, another prediction of general relativity, arises from the curvature of spacetime near massive objects. The magnitude of this advance depends on the masses of the two stars and the orbital parameters. By combining measurements of the mass function and the advance of periastron, the team estimated the mass of the pulsar to be approximately 1.44 solar masses and the mass of its companion to be approximately 1.39 solar masses. These masses were consistent with those of neutron stars. The exact nature of the companion remained uncertain at the time, but the authors speculated that it could be another neutron star, a white dwarf. The precise measurement of the advance of periastron supplied critical data for refining mass estimates. Section 6. Discussion of alternative explanations. Hulse and Taylor comprehensively addressed alternative explanations for the observed orbital decay before concluding it constituted evidence of gravitational waves. They meticulously examined the potential influence of tidal effects, mass transfer between the two stars, and the presence of unseen third bodies. Each of these possibilities was carefully evaluated and ultimately deemed insufficient to account for the observed rate of orbital decay. Tidal forces arising from the gravitational interaction between the two stars could alter the orbital period, but the predicted effect was much smaller than the observed change. Similarly, mass transfer, the flow of matter from one star to the other, could also affect the orbital period, but there was no observational evidence for ongoing mass transfer in the system. The authors also considered the possibility that the observed orbital decay might be attributable to the presence of a third, unseen star orbiting the binary system. However, detailed calculations showed that such a scenario was highly unlikely and incompatible with the observed timing data. By systematically ruling out these alternative explanations, Hulse and Taylor strengthened their argument that gravitational wave emission was the most plausible interpretation. The rigorous examination of alternative hypotheses enhanced the paper's strength and credibility. Section 7. Implications for general relativity and astrophysics. In the concluding segment, Hulse and Taylor considered the broader implications of their discovery for general relativity and astrophysics. They emphasized that the binary pulsar system provided a unique laboratory for testing general relativity in the strong field regime, where gravitational effects are exceptionally strong. The observed agreement between the predicted and observed rates of orbital decay represented a striking confirmation of Einstein's theory. The discovery also had significant implications for understanding the evolution of binary star systems and the formation of neutron stars. The existence of a binary system containing two neutron stars suggested that such systems might be more common than previously thought. The system offered insights into the processes by which neutron stars are formed and how they interact with their companions. Furthermore, the discoveries spurred the development of new techniques for detecting and studying gravitational waves, paving the way for future gravitational wave observatories. The work highlighted the importance of continued observations of the binary pulsar system to further refine our understanding of general relativity and the physics of compact objects. The discovery fundamentally shifted the landscape of gravitational physics and astrophysics. Section 8. Subsequent observations and refinements. Following the 1975 publication, continuous monitoring of Pulsar B19-13+16 yielded even more precise measurements of its orbital parameters and the rate of orbital decay. These extended observations bolstered the initial conclusions and provided further support for the general relativistic prediction of gravitational wave emission. Later refinements incorporated improved timing models, more sophisticated data analysis techniques, and a deeper understanding of the interstellar medium. These subsequent analyses reinforced the initial findings and solidified the importance of the binary pulsar system as a crucial testbed for general relativity. The long-term observational campaign demonstrated the power of sustained scientific inquiry in unraveling the mysteries of the universe. Section 9. Confirmation With advanced instruments, the launch of space-based X-ray observatories, and advanced radio telescopes further enhanced observations of PSR B1913+16 and similar binary pulsar systems. These instruments delivered data across different regions of the electromagnetic spectrum, providing a more complete picture of the system's behavior. X-ray observations offered insights into the environment surrounding the pulsar, while improved radio telescopes delivered more accurate timing measurements. The combined data from these diverse instruments confirmed the general relativistic predictions with ever-increasing precision. The convergence of evidence from multiple observational platforms solidified the scientific consensus regarding the existence and properties of gravitational waves. This interdisciplinary approach underscored the importance of combining different observational techniques to probe complex astrophysical systems. Section 10 Gravitational Wave Astronomy and the Legacy of PSR B1913+16, the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, marked a new era in astronomy. The initial discovery of PSR B1913+16 laid the groundwork for this groundbreaking achievement, by furnishing the first indirect evidence for gravitational waves and validating the theoretical predictions. The binary pulsar discovery also stimulated the development of advanced data analysis techniques and fostered a deeper comprehension of the sources and properties of gravitational waves. The success of LIGO and other gravitational wave observatories is a testament to the enduring legacy of Hulse and Taylor's pioneering work. Their discovery opened a new window on the universe and transformed our understanding of gravity and the cosmos. The binary pulsars served as a crucial stepping stone in that journey towards gravitational wave astronomy. Section 11 Theoretical Implications and Cosmology. Beyond directly verifying aspects of general relativity, the discovery also stimulated theoretical research. Specifically, the confirmation of energy loss through gravitational waves provided indirect but powerful data about the behavior of black holes, dark matter, and the expansion of the universe. Theories positing altered behavior of gravity at galactic scales, for example, faced new scrutiny, as the binary pulsar's behavior conformed so precisely with predictions derived from Einstein's equations assuming a uniform gravitational constant. The work also had significance relating to constraints on modified theories of gravity seeking to explain dark energy. The existence and properties of the Hulse-Taylor binary system provided unique insights into the nature of gravity across vast distances and diverse cosmological epochs. Section 12 Technological Echoes and Signal Processing Advances. The challenges of accurately timing the pulsed emissions of PSR B1913+16 spurred development in signal processing techniques. The necessity of separating a pulsar's signal from background noise and interstellar scintillation forced innovation in algorithms for time series analysis and spectral estimation. These advancements found a wider application in fields related to radio astronomy, radar systems, and communication technologies. The discovery, therefore, led to a ripple effect, improving technologies far beyond the realm of astrophysics. The relentless pursuit of precision in astronomical observation drove technological innovation, benefiting various fields. Section 13. The broader significance of indirect detection. The indirect detection of gravitational waves through the observation of orbital decay underscores a crucial aspect of scientific methodology. Even in the absence of direct observation, one can still infer the existence of phenomena through their effects on other observable systems. This principle has broad application across various disciplines, from particle physics to climate science, and provides a framework for exploring phenomena beyond the direct reach of current observational capabilities. The binary pulsar discovery exemplified the power of indirect detection in furnishing evidence for elusive physical processes. Section 14 Contextualizing the discovery. Within the Cold War era, it is pertinent to remember that the discovery occurred during the height of the Cold War, a period marked by intense scientific competition between the United States and the Soviet Union. The fact that the discovery was made at the Arecibo Observatory, a US-funded facility, highlighted the role of scientific research as a symbol of national prowess and technological advancement. The discovery fueled a spirit of scientific innovation and competition. It became a demonstration of American ingenuity. In conclusion, Hulse and Taylor's discovery of the binary pulsar PSR B1913+16 stands as a pivotal achievement in 20th century physics. Their meticulous observations provided compelling evidence for the existence of gravitational waves and constituted a rigorous test of general relativity in the strong field regime. The work led to a revised understanding of how these types of celestial objects behave. Further study led to the advancement of astrophysics and technology. The impact extends far beyond the initial detection, shaping the course of gravitational wave astronomy and influencing cosmology and fundamental physics. The system continues to serve as a powerful reminder of the elegance and predictive power of Einstein's theory and its relevance to understanding the workings of the cosmos.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.